everyone, welcome back. So today I am going to be doing the part 2 of stoichiometry, and we left these two questions last time. Apart from this, I will be solving two more major questions from past papers so that we can do a little bit of stoichiometry practice. Okay, so let's start with this first question. Camphor is a white solid which was used to make the early plastic celluloid. Camphor contains the same percentage by mass of hydrogen and oxygen. What we're going to do is, first of all, I'm going to show you how to actually calculate empirical formula. So let's assume, this is unrelated to this question, but let's just assume, so I'm going to draw carbon, hydrogen, oxygen, and we are going to assume, because this says same percentage by mass of hydrogen and oxygen, I'm going to take 30% hydrogen, 30% oxygen. Then I'm left with 40% for carbon. Now, what we do when we have to calculate the empirical formula, suppose we were given a question where we were told that there's a compound that contains only carbon, hydrogen, and oxygen, and they gave us the percentages of mass occupied by those elements in that compound, and we were told to find the empirical formula. What you would do, first of all, you have to assume that, so first of all, you have to assume that the compound is 100 grams, because if you have these percentages, right, you're going to assume that these percentages are out of 100. So for example, we're going to assume that 40% of carbon is actually 40 grams of the compound from this 100 grams. So that's what you're going to do. So I'm just going to put that to the side. So we assume that the compound is 100 grams. Then what we do, now since it's 100 grams, I'm just going to rewrite the percentages as masses. This is what we have. Now carbon has an atomic mass of 12, oxygen has 16, and then hydrogen has 1. According to the periodic table given to you at the end of every question paper, these are going to be your atomic masses, relative atomic masses. So what you have to do is, when we're calculating the empirical formula, we're basically determining the ratio of these elements to each other. So you are going to divide these elements, each of them, by their atomic mass. So carbon is 12, so we have 12 here. Hydrogen is 1, oxygen is 16. When we have this, for carbon, what I get is 10/3. Hydrogen would be 30, and then oxygen would be 30/16. That's 15/8. What we do now is, you can do two things. You can simplify this ratio as much as possible. Some people like to do this by cancelling out, by multiplying, like let's say we have 3 here, so we multiply this whole ratio by 3, and then you would get 10, 90, and then this would be, I believe, 45/8, if I'm not wrong. So that's basically what some people like to do. You could also divide these three by the lowest number amongst them, and then work your way for the ratio. It's basically the same thing. I usually prefer to do it this way, but you can do it however you like. If we do it by dividing the ratio by the lowest number. The lowest number is 10 over 3. So if we do that, what we're getting is 1 is to, hold on, 30 divided by 10 over 3, that's 9 over 16. And then you would eventually have to multiply everything by 19 so that you get the simplest possible ratio. So you would get 16 by 144 by 9. If you simplify this ratio by multiplying this thing by, let's say, 8, because we have 8 here, you would get 80 is to 720 is to 45, and then simplifying this by dividing it by 9, sorry, by dividing it by 5, my bad, you would get 16 is to 144 is to 9, which is the same thing. These are the same thing. And once you get this final ratio, your empirical formula would be carbon, which is 16, hydrogen, which is 144, and oxygen, which is 9. That would be your empirical formula. And that is how you calculate an empirical formula from given percentages of mass. Now, what we have here is, this is the only information we have, same percentage by mass of hydrogen and oxygen. So when we're determining the molecular formula, we're going to do the reverse. And now, how do we do the reverse? I'm gonna use this as an example. So we have 10 is to 6 is to 6. This is the ratio. This is the beginning step here. That's what we're given. So that's the ratio that we have. I'm just going to simplify this a bit further. You can divide these by 2 and you get 5 is to 3 is to 3. Now, as you can see over here, we actually divided the masses by their atomic mass. So what we're going to do is we're going to multiply, because multiplication is the reverse of division. So we're going to multiply. Now this is for carbon, so you multiply it by 12, you're going to get 60. This is hydrogen, so multiply by 1, you get 3. This is oxygen, multiply by 16, and you get 48. These percentages do not add up to 100, but the main principle behind this is the hydrogen and oxygen need to be the same, which they are not. So we can successfully move on to the next option. For B, we have 10 is to 8 is to 0. Is to 1. So we're going to multiply these. It's already in the simplest ratio. We're just going to multiply them by their atomic masses. So that would make this 120 because you're multiplying by 12. This would become 8 and this 16. Again, the percentages do not add up, but what actually matters is hydrogen and oxygen have to be the same, which they are not. So now let's move on to option C. We have 10 is to 16 is to 1. So multiplying carbon, you get again 120. Hydrogen, multiply by 1, you get 16. And then oxygen, multiply by 16, you get 16. We have a match. So our correct answer would be C. And that is how you work through a question like this. It's good to revisit the basics by this kind of a simple example and then use this example to navigate how you would do the opposite, because that is what the question is asking you to do. Now that we have that done, let's move on to the next question. So in leaded petrol, there is an additive composed of lead, carbon, and oxygen only. This compound contains 29.7% carbon and 6.19% hydrogen by mass. What is the value of X in the empirical formula? PbC8Hx. So we're given the empirical formula, but the goal of the question is actually to sort of find it. So I'm just going to write the elements down. This is what we have. And first of all, you need to determine the percent of lead remaining, because the compound has only lead, carbon, and hydrogen. And we've already been given mass of hydrogen, and percentage mass of carbon. I had to swap those, my bad. So once we know these, we're going to calculate for lead. Lead percentage would be 100 minus 29.7 plus 6.19, that is 64.11%. So I'm just going to write that down. 64.11%. Carbon is 29.7, and then hydrogen is 6.19. So now the next step is to divide these by their atomic masses. Hydrogen is 1, carbon is 12. For lead, we need to check our periodic table, and lead is here. Its atomic mass is 207.2. So that is what we have. And for lead, I'm getting 0.3094. Then carbon is 2.475. Hydrogen is 6.19. So now what we can do is divide everything by 0.3094. Since it's in decimal form, you don't really know what to multiply the figures by so that you get a clean, let's say, whole number of ratios. So it's best to just divide by the lowest number. It helps simplify your empirical formula. So over here you're going to get 1, and I'm assuming, because in the empirical formula given the lead already has a value of 1, this is going to be the simplest ratio already. So this would be 1. This is actually 7.999. And what we get for hydrogen, which is what we're looking for, is 20.006. So therefore, when I simplify this, I'm gonna get PbC8H20. So our answer for this question is D. And that's how you do it. So that's for this. That's for the notes. We're done with the 2 last examples that I had. Now let's move on to an actual worksheet. Okay, so we have spathos is an iron ore that contains iron 2 carbonate FeCO3. The percentage of iron 2 carbonate in spathos can be determined by titration with acidified potassium dichromate solution using a suitable indicator. The ionic equation is shown below. We are given this beautiful equation here, and for what it's worth, a 5-gram sample of spathos was reacted with excess concentrated hydrochloric acid and then filtered. The filtrate was made up to 250 cm3 with distilled water. Okay, so a 25 cm3 sample of the standard solution required 27.30 cm3 of 0.0200 moles per dm³ dichromate solution for complete reaction. Our first question is to calculate the amount in moles of dichromate ions used in the titration. So the formula that we are going to use, because what we have been given is concentration and volume. We've been given this volume and this concentration. So we are going to use this formula, concentration by times volume, which is moles. So our moles, which I'm going to represent by N, is C times V. Our C is 0.0200. Our volume. Now our volume is given in cm cubed, but over here you can see the unit for the concentration has dm cube in it. So we're supposed to convert the cm cube to dm cube. How we do this is the conversion unit is basically 1000. So 1000 cm cubed is equal to 1 dm cube. That's what we're going to use as our conversion factor. So 27.30, we're just going to divide it by 1000. This should give us our mole. And what we get is 5.46 times 10 to the power minus 4 moles. That is what we're going to write here. This is to the correct number of significant figures because all the significant figures we've been given so far, even in the question. As you can see, this is 5.00 grams, 25.0. It's all 3 sig figs, and that is the exact answer we got. So it's a good thing. All our answers should be to 3 sig figs, which is the same amount of significant figures you use to achieve your answer. So the second part says use your answer to I to calculate the amount in moles of Fe2 plus present in the 25 cm cube sample. So for this we have to use mole ratios. We have the amount of dichromate ions. Now the dichromate ions are present here in the equation, and this is the Fe2 plus ions that they want us to find. The ratio, as we can see here, for every 1 mole of dichromate ions, we have 6 moles of Fe2 plus reacting. So our ratio is 1:6. So if we have 5.46 times 10 to the power minus 4 here, over here we're supposed to have 6 times that amount. And what we get is 3.276 times 10 to the power minus 3 moles of Fe2 plus. So, but the amount that we would put in is 3.28 because we need to write it in 3 significant figures. So that is our answer. However, when we're doing calculations in the questions later on, we will use this figure because it's more accurate. Until the final answer isn't said, you have to use the figures you had before. So use your answer to II to calculate the amount in moles of Fe2 plus present in 250 cm cube of the volumetric flask. Now remember, this 25 cm cube sample was taken out of 250. So this is basically like 10% of the total amount. So this is 10% of the mole that is in the actual volumetric flask that we had. So how we're going to calculate the amount of moles in the 250 volumetric flask is we're just going to multiply this, the one in the 25 cm cube, by a factor of 10, because, or to make it simpler visually, I'll just do 250 over 25 because that is the factor you're going to multiply it by. Suppose this wasn't 250 and this was 200. and we took 25 out of this, then you would have to make the 250 here into 200, but that's not the case. So what we're gonna get is 3.28 times 10 to the power minus 2. So that's what our answer is going to be. Now use your answer to II to calculate the mass of iron 2 carbonate present in the sample of spathos. For mass, the formula we are going to use is this one: moles equal to mass over molar mass. So I'm just going to write the formula down. N equals mass over molar mass. This would be formula mass, but I'm just going to say MR. First of all, we need to calculate the MR of iron 2 carbonate. So our MR of FeCO3. This is the sum of the atomic masses for these atoms. So the atomic mass of iron is 55.8. So we have 55.8 plus carbon, which is 12.0. Oxygen is 16, but we have 3 atoms, so we multiply that by 3. What we get is 115.8. So now we are going to calculate the mass. When you rearrange this formula, the mass is basically the mole times the molar mass. So our answer is actually going to be, our answer is going to be 3.2. I'm going to do 276 over there. 3.276 times 10 to the power minus 2 multiplied by 100. Oh my god, sorry. This is not supposed to be in grams. This is actually grams per mole. I don't know why I did that. I'm so sorry for that mistake. So we have 3.276 times 10 to the power minus 2 times 115.8. So our mass is going to be 3.793608 grams. That's a very long figure, but I'm just going to simplify it to 3.79 grams. That's going to be our mass. Now we're told to calculate the percent of iron 2 carbonate in the sample of spathos. Spathos is the ore that we had, and it has iron 2 carbonate, which we just calculated its mass, 3.79. So the mass of the sample was 5 grams. Hence, our percentage of iron 2 carbonate would be the mass of the iron 2 carbonate over the mass of the ore that we used to extract that iron 2 carbonate times 100. And this is 75.9%. I actually, in my calculator, divided this by, I divided this whole thing by 5, and what I got was actually 75.87%, but you can just simplify to 75.9 because it's supposed to be to 3 significant figures. So that is our percent of iron 2 carbonate. That is for the calculation part of this question. We have an ionic equation part and some other stuff. So iron ores can be analyzed using a similar method. A standard solution of an aqueous iron 3 compound is reacted with aqueous tin 2 chloride. Aqueous tin 4 chloride and aqueous iron 2 chloride are the products of this reaction. We're supposed to write an ionic equation and no state symbols. Okay, so first things first, we have an iron 3 compound, We don't know what compound this is, but we do know that it has iron 3 in it. So first thing we would write is Fe3 plus. That is the ion that is present in that iron 3 compound. It's reacted with aqueous tin 2 chloride. The ion present in aqueous tin 2 is Sn2 plus, which is tin 2 plus. And the products that we get are aqueous tin 4 chloride. So we have Sn4 plus, and then aqueous iron 2 chloride. So we have Fe2 plus. As you can see, the charges are not balanced. So what we need to do is balance these charges. It's the same as kind of balancing an equation. So over here, what we can do actually is we can balance the iron. Over here I'm just going to put a 2, that would make this 6 plus, and I'm going to put a 3 here. That would make this 6 plus as well. Oh, hold on. It doesn't, because this should rather be 2. You know why? We have 6 here, 6 plus, and then 2 plus. So we have 6 plus, 2 plus. That becomes 8 plus already on the left side. And over here we have 4 plus. And with the 3 here, it was going to be 4 plus 6. That would have been 10. And we could have fixed that by putting a 2 here. But then that would just be a bit too messy. And this is much cleaner because we only have two numbers in front of the ions. Otherwise we would have had 3 different numbers, a 2 here, a 2 here, and a 3 here, which is not wrong, but it's just too much work. You can do that if you feel like it. There's always different methods of getting an answer, and it would be the same. But this is always supposed to be the simplest way you can put it. So that's for that part. And what we have here is any excess tin 2 chloride can be removed by reaction with HgCl2, which is mercury chloride. A white precipitate of Hg2Cl2 is produced. Complete the equation. So the first thing we have is aqueous tin 2 chloride. That is this compound, and it's aqueous. So I'm just going to put that there. We know that the Hg2Cl2 is a precipitate. Precipitates are usually solid, so I'm just going to put solid there. SnCl4 is aqueous, as said here, aqueous tin 4 chloride. And over here, we need to put 2 because there's 2 mercuries. So that completes this question. This is the first question of the worksheet, and we're done with that. Okay, so the next question we have is acidified potassium dichromate can oxidize ethane dioic acid. The relevant half equations are shown. We have our half equations. Okay, state the overall equation for the reaction between acidified dichromate ions and ethane dioic ions. So we haven't done this yet, but basically what you're supposed to do is add these equations, sort of like an algebraic equation. As you can see, there's 6 electrons here, 2 electrons here. This 6 electrons is on the left hand side of the first equation. 2 electrons are on the right hand side of the second equation. But in the final equation, we're not supposed to have a single electron present. So what we can do is multiply this entire equation by 3 so that we get 6 equations here. And when we add this, I'm sorry, we're supposed to subtract, not add. When we subtract these two equations, we get no electrons on either side. So I will just put the 3. So we have 3 here, and this would change to 6, this would change to 6, and this would also change to 6. Alright, so when we're forming our final equation, what we have is Cr2O7, 2 minus, and then plus 3H2C2O4. Now, at the left hand side of this, we now have 6 hydrogen ions and we have 14 H plus here. So we need to subtract them. So that would become 8 H plus. And then we have basically nothing left on the left hand side because this 6 electron would subtract with these 6 electrons. So our right hand side would give us, our right hand side would give us 2 Cr3 plus 7 H2O plus 6 CO2. That is what we get. And that is our overall equation. So the B part states that in an experiment, a 0.242 sample of hydrated ethane dioic acid was reacted with a 0.0200 mole dm cube solution of acidified potassium dichromate. 32 cm cubed of the acidified potassium dichromate solution was required for complete oxidation of the ethane dioic acid. Calculate the amount in moles of dichromate ions used to react with the sample of ethane dioic acid. So the dichromate ions, our volume is 32 cm cube, which is actually 3.2 times 10 to the power minus 2 dm cube. Our concentration of the dichromate solution is 0.0200. So when we're calculating the moles, we're going to use the same formula, N equals C times V. So we're going to have 0.02 times 3.2 times 10 to the power 10 to the power minus 2. What we get is 6.4 times 10 to the power minus 4. So 6.4 times 10 to the power minus 4. I'm just going to put 0 here so that we know it's in 3 sig-figs. So calculate the amount in moles of ethane dioic acid in the sample. Our ethane dioic acid is with a ratio of 1:3. So we're going to multiply the moles of dichromate ions by 3 to get our moles of ethane dioic acid, just as we did in the previous question with the iron carbonate. So going to multiply this by 3 and I get 1.92 times 10 to the power minus 3. That's the amount of moles of ethane dioic acid in the sample. So calculate the relative molecular mass of the hydrated ethane dioic acid. So we have the moles of the acid, that is 1.92 times 10 to the power minus 3. I believe we have its mass, which is 0.242. So 0.242. So the relationship between these three uh, stoichiometric principles is we have our mole, which is our mass over our molar mass. So when we rearrange this, molar mass is mass over moles. This is 0.242 divided by 1.92 times 10 to the power minus 3. So our molar mass is actually 1.26.04. I'm going to write 1.26.0. That's our molar mass. And now we're supposed to calculate the value of X in H2C2O4 times, point X H2O. What we have to do here, we have the molar mass of this entire compound. That is 126.0. The molar mass of water is actually 18. So what we have is 18 times X. And then we have 18 times X plus H2, the molar mass of H2C2O4 is equal to the total, which is 126.0. In calculating this, the molar mass would be 2, which is 1 times 2 for the hydrogen, plus 24 for the carbon, plus 64 for the oxygen, and that is, that is 18x plus 90, which is 126.0. We will have 18x, which is 36, and so we can divide both sides, and what we're going to be left with is 2. So x is 2, and that is how to solve questions related to these hydrated sort of compounds. So I've done questions with empirical formula, molecular formula, percentage mass. We've done hydrated compounds, and we've practiced the basic formulas of N equals C times V and N equals M over MR, and we've done a few examples and calculations of our molecular mass and our moles. And we've done a few conversions too, from cm cube to dm cube. We've also practiced how to write ionic equations and how to balance them. So our goal for today is done, and I'm done for the day. I hope you guys really enjoyed these. I am not, the barcodes are not supposed to be shown, so I will write down the links. I will write down the papers, the years that they are from, and the question, the question number. So you can check the mark scheme for further help or confirmation. And that is it. I hope you guys found this video very useful. It's actually supposed to be practice. The entire worksheet is filled with questions of these similar types, so I only picked the best two that were different topics, because the others are virtually the same. It's just for more practice. And yeah, I hope this was worth your time. I will be putting timestamps again as usual in the description. Please leave a comment for any further explanation, or if I did something wrong, please feel free to correct that. I will be posting more worksheet videos, and videos will be more consistent from now on. Sorry for the delay. Thank you guys for your patience, and I hope to see you soon. Bye.